Welcome to the ChemDoctor, and this is the third video in the series on the Bohr model. Now, what I highly recommend is that you watch the first two videos that I've produced that deal with this particular concept area. The first video was called Simulation of an Electron Binding to a Proton, that dealt with the idea of electrostatic force of attraction between the proton and the electron, and then Intro to the Bohr model, video number 1, which lays out the groundwork for this video, because what I do in that presentation is discuss the idea again of electrostatic force of attraction between the electron and the proton, and the relationship to electrical potential energy. All right, so to get started, basically what we need to remember here is the relationship between the proton and the electron. So I'm going to show it this way. I'm going to have a proton here, and then I'll put my electron very close by, and they're going to be separated by what in the Bohr model we call an energy level, and I'm going to call this particular energy level N1. Now, the way I'm going to visualize the Bohr model is through a ledge cliff system, and the thing that you need to remember about this is that I'm describing the energy relationship between an electron and a proton utilizing a model. So this is not exactly, in fact, it's not at all how the electron is related to the proton in an atom, because the electron does not have a physical space where it lives. But the issue here is that if you're in a first-year chemistry class or university level general chemistry, you've got to learn what the relationship is in terms of energy and the electron, and this is a really good way to think about it for a while. And the way that I'm going to describe this is through a ledge cliff system. So the main premise of the Bohr model, which still holds up today, is that the electron has only specific energy levels that it can exist in, and it cannot exist anywhere between those energy levels. So I'm going to describe the energy platform of the electron using a ledge cliff system. So the very first energy level that we have is going to be the one where the electron is closest to where the proton is. And the Bohr model was described for hydrogen, but you can extend these ideas to the other atoms in the periodic table by simply understanding that you're going to have to add more protons here instead of one, and obviously there will be more electrons. But for simplicity's sake, we're going to only consider this on the level of hydrogen. Now, when I say that you can just extend the model to the other atoms, what I'm saying there, to be clear about it, is extending the idea that electrons have only specific energies that are allowable, and electrons do not exist between those allowable energies. And again, I'm going to use a ledge cliff system to describe that. So the next energy level up from the electron will be here, and we're going to call this N equal 2. An N level being simply an allowable energy state for the electron. All right, and the next one up we're going to call N3. Now you're going to notice that my ledge systems are each ledge system is getting closer to the next higher energy level, and this is how we see the quantum mechanical model lays out the energy levels for an atom, and there are a total of 7 energy levels that take care of all the electrons for any of the elements that are in the periodic table. So this is how I'm going to lay out my system of energy levels. And again, you see my cliff systems here. The electron cannot exist anywhere on that cliff system. It'll just simply fall back down into whichever ledge system is below it. So the electron can only exist on these ledge systems and not between them. Now, what led Bohr to establish this model? And to understand that, we need to go back and do somewhat of a history lesson here, but not anything long and drawn out. So in the upper left-hand corner of my video, I'm showing light spectrums. And the top one is a continuous line spectrum. The word continuous means that in this particular light spectrum, we are showing all the possible wavelengths of light. And specifically here, we're only showing the visible spectrum because those are the light waves that we can see. There are light waves that are part of the electromagnetic spectrum that we can't see. Like up here on this end of the spectrum, we have ultraviolet light, we have X-ray radiation and gamma radiation. And down here on this end of the light spectrum, we're going to have the radio waves and infrared radiation and so on. Up here on the left end, where we have the blues and the violets, this is high energy light. I'm just going to abbreviate energy like that. And down here on this end of the spectrum is low energy light. And I'm assuming as you watch this video that you understand enough about light to get the fact that all light has energy, and we can write a simple formula like this one. So the energy of a light wave, or the energy of a photon, is equal to Planck's constant times the frequency. All right, this is also equal to Planck's constant times the speed of light in a vacuum divided by the wavelength. All right, and let me go ahead and define some of these in words so that you don't forget. So the little v here is frequency. It's actually the symbol nu. All right, and c is for speed of light, and this is speed of light in a vacuum. All right, and then the lambda thingamabobby here is your wavelength. And a quick primer on this, we can draw a simple wavelength like this. And I'm going to define my distance through here as a 1 second interval. The wavelength is literally, if I took out a ruler and measured from the top of the peak, this peak here to this peak here, this would be my lambda or wavelength. And if I count up my peaks in this interval, we've got 1, 2, 3, 4. So there are a total of 4 peaks. And the interval is exactly 1 second, and this is our frequency. So I think normally in a physics class they're going to call this hertzes. In a chemistry class too, but whatever. I want to keep things easy. So the wavelength is moving through here at constant speed, speed of light. The wavelength is simply the distance between the tops of the peaks. If we have a 1 second interval, then we can count up the peaks, and there are 4 peaks per second. So all light has energy. Light of different wavelengths have different energies. Now, what does this have to do with the Bohr model? All right, so back in the day, Einstein was taking various metallic substances and irradiating those substances, or shining light of specific wavelengths on those substances, and seeing that light of certain wavelengths could eject electrons from certain substances, a very specific thing. The light of a certain wavelength could eject electrons from one substance but not another. And this suggested to Einstein that electrons had specific energies. Bohr, on the other hand, and another guy named Rydberg were taking substances like group 1 metals, group 1A metals like sodium, lithium, potassium, just as an example, calcium, strontium, barium, and they were submitting those elements to another type of energy, like heating them up. They would take these particular substances, or the salts of these substances, and put them in a flame, and then observe what happened next. And what they learned was that these substances were producing light, but the light that they were producing was a very specific type of light, light of a singular wavelength. And so Bohr looked at those results and determined that since these particular substances, when agitated by heating them or running an electrical current through them or something that had energy, when you energize these substances were glowing, but they were producing a single wavelength of light. And he deduced from this that if these substances, when agitated, were producing a singular wavelength or a singular wavelength of light, that the electronic transitions that were happening had to be specific in energy. And from that came his model. And so I am diagramming my particular model that explains what Bohr was trying to communicate. So this is the idea. We have an electron in hydrogen that is sitting as close as it can get to the proton. We're defining this energy level as n equal 1. This is the level where the electron is most stable because it is closest to the proton. Now, what I want to do here is draw a reference line. And I'm going to add some information here, so as we go along, it makes it easier for the viewer to understand, what the heck we're talking about here. So the first thing I'm going to do is draw an arrow that indicates distance. And distance is increasing in the direction that I've drawn the arrow. So as we move from N1 towards N7, the electron is getting further away from where the proton is. The next thing I want to do is bring in the idea of potential energy. And this goes back to the video that I produced before this one, Intro to the Bohr Model #1. So we're going to call this potential energy. And it's increasing again in the direction that the arrow is drawn in. And then what I want to do to help you relate to this is draw another arrow here pointed towards the direction of the proton. And this is force of attraction. So as the electron gets closer to the proton is holding it more tightly. And this is why the potential energy diagram is drawn in the direction that it's drawn in. As we move the electron towards the proton, force of attraction increases, so the electron is actually at lower potential energy the closer it is to the proton. Now for hydrogen, we call the state where the electron is closest to the proton the ground state. Now you have to be careful extending this idea of ground state to any other atom, because hydrogen only has one electron. Helium has only 2 electrons. So the ground state for helium and hydrogen is going to be N1. But any other atom on the periodic table is going to have more electrons than this. And you need to realize that the ground state for those particular atoms is going to be one that involves more energy levels than just N equal 1. All right, now, how does the Bohr model work? All right, so let's go back to the idea of what Bohr and Rydberg did. So let's say we have some hydrogen, and we take it and we energize it by putting it into a flame. All right, and what these guys see when they did stuff like that, again, they're energizing the electron, they're energizing the atom, and when they do that, what they see is a change in the coloration of the flame if we're holding that electron in a flame. Now, granted, hydrogen is a gas, and we're not going to be really holding hydrogen in a flame. But with these metallic substances, like the ones that I listed here, you can take the salts of these and indeed put them into a flame, and then observe what happens to the coloration. And when you do that with sodium, what you're going to see is a brilliant yellow flame. With lithium, it's going to be a brilliant red flame. With potassium, it's going to be a purplish flame. Calcium is sort of a dirty orangish brown flame. Strontium is more reddish like lithium, and barium is sort of silver green. My point being is that when you energize these salts, you see very specific colorations coming back out of the flame. So what explains this? So the idea is you can energize the electron, and when you energize it, if you put in the right amount of energy, that electron can be moved to a higher energy level. The idea is that the electron can only move to a higher energy level if you put in exactly the energy difference between the energy level that it's leaving and the energy level that it's going to. So basically, I'm going to go ahead and draw another line here, a horizontal line going up like this, and we're going to just establish that this is energy in general. And you can see that if I draw a line here for where the ledge system is for N2, that it would be E2, and the energy for the platform 1 is E1. So if I want to move the electron from N1 to N2, at minimum, I'm going to have to put in the energy difference between N1 and N2. Otherwise, the electron can't go up here. I mean, you can think of it this way. If you put in only a partial amount of energy, then the electron is going to move up the platform a little bit here. But since there's no ledge system here, it's just going to bounce back down to its original location. And again, this is a reasonable way to think about it. But again, in atoms, there aren't really cliff systems. But I like this model because I think you can visualize what's going on here. So the only way to get that electron up here to N2 is by putting in a minimum of the energy difference between these two platforms. Now, we could put in enough energy for that electron to go from N1 to N2, or if we wanted to, we could put in enough energy to move that electron all the way from N1 to some other energy platform or ledge system, perhaps up here to N4. Again, keeping in mind, see, that we have to put in a minimum of the energy difference between those two energy levels. Now, once the electron is up here, the electron and this particular atom is in what we call an excited state. All right, and the electron is not going to stay here because it is at a level of higher potential energy. Again, if we draw a dotted line across here, you can see that we're in an elevated platform. We're at higher potential energy. The force of attraction between the proton and the electron is less, and so on. The electron is not going to stay here. Given an option, it's going to move back down. Keep in mind that if we're doing a flame test, all right, so we're maintaining this metal salt in a flame, there is plenty of energy here. So that is around. So this electron actually has several options here. There's enough energy to move it into a higher energy level. The atom is in an excited state. The electron could also move down. Now, if we have this electron in N4, look at the options it has to move down. It could move from N4 into N3, for example, or it could drop down to ledge number N equal 2, or it could drop all the way back to N equal 1. Whatever happens, all right, say it drops from N4 into N3, all right, it will have to release the energy that it gained in N4, dropping back to N3, so it has to drop the energy difference between where it's starting and where it's ending. If it goes all the way back to N1, then it's going to have to literally drop the energy that it gained moving to N equal 4 all the way back down to N equal 1. And that energy that comes off is going to be released as light. So the energy is going to be released as light. Right? I'm going to put that in words. So the energy is going to be released at light. So now what I want to do is draw your attention back up here to these two spectra we haven't really talked about yet. So let's first discuss this lower spectrum that's called an absorption spectrum. All right, these are absorption lines, but this is called an absorption spectrum. So remember, you can cause electrons to move from a lower energy ledge to a higher energy ledge using any kind of energy source. So instead of using a flame to elevate the electron to a higher ledge system, we could have used light to do it, because remember that that light has energy, just like a flame has energy. So let's go back to our diagram here for just a second. Let's say that we moved our electron from N1 to N4 using light energy to do it. So if you look at the absorption spectrum here, you can see that it looks just like the continuous spectrum, except there are these black interruptions. These black bands are the absence of light, and what these black bands indicate is that this particular wavelength of light, I'm going to focus on this one, is missing because that particular band of light was used to elevate an electron. And I'll just stipulate this in my diagram. We'll just say, for pretend, that this band of light was used to elevate an electron from N1 to N4. So you see the absence of light here in this band because that energy was used. It was used or absorbed by the electron to move it from N1 to N4. And then when the electron jumped from N4 back to N1, that same energy was released, and it was released as light. And you can see when you look at the emission spectrum that is right above the absorption spectrum, you see the appearance of that exact band of light. All right, let me be more specific about it. I'm going to draw an arrow to it. So you see the emergence, literally, of that band of light right here. And that is the light that is being released because the energy that was used by this electron, that was absorbed by this electron to move it up the cliff system to N4, is now released when the electron moves back down to N1. And it comes off as a specific band of light that has a specific wavelength, and you can see it. So the emission lines here literally are electrons jumping back down from a high ledge system to a low ledge system. The bands that you see in the absorption spectrum here, the blackness that's interrupting the continuous spectrum, represent lines of light where the wavelength, the energy of that wavelength was actually absorbed by an electron to move it from a low ledge system to a high ledge system. All right. So again, the take-home message here is that electrons in atoms have only specific energy levels where they exist. To move an electron from a low ledge system, a low energy system, to a higher energy level requires the absorption of, at minimum, the energy difference between those two energy levels. You can use more energy than needed to do that transition. Once the electron gets to the new energy level, it will have the energy of that energy level plus the excess's kinetic energy. All right. Now, once the electron is in a higher energy level, it can move back down to a lower energy level. When it does that, the energy that it gained getting to that upper energy level is going to be released as light. And we see that light as a very specific wavelength of light because the energy difference that's released when the electron jumps back down is released as a single band of light given by this equation. Okay, now I would like to thank the viewer for watching this video and just remind you that we're talking about a model here, and my cliff system in no way represents the actual story of the electrons in an atom, because electrons do not have physical locations. But this is a reasonable way to think about the energy structure of an atom. The key thing to remember is that electrons have specific energy levels where they can exist, and they cannot exist between those levels. The electron can be moved from a lower energy level to an upper energy level by putting in exactly that energy difference. When the electron moves down, it will release that energy as light. All right? Thank you very much for watching.